Okay, in this first video on Hess's Law, we're going to show how you can calculate the enthalpy changes indirectly for a process. And it's very important that we can do this because for some reactions we cannot physically we cannot physically measure the enthalpy change. Maybe you get more than one product being formed. For example, if you mix a carbon and hydrogen together to form a specific alkane, you'll end up getting a mixture of alkanes. You might have a reaction which has got a very high activation energy. So, so we need a different way to do this. And Hess's law states that for any chemical change, the enthalpy change is the same regardless of the route taken. So, we're showing this here in this reaction between A and B. The enthalpy change here is minus 200 kilojoules per mole. But what we are thinking is that perhaps we could get from A to B going via C, and then from C to B. Oh, just show my arrowhead in there. So the reaction A to C has got an enthalpy change value of minus 120 kilojoules per mole. The reaction C to B has got an enthalpy change of minus 80 kilojoules per mole. Because the direction that we are going in, i.e. we want to go from A to B, is the same as the arrow directions for A to C and C to B, then we add the two reactions together. So our value is minus 120 plus minus 80 equals minus 200, and that is exactly what we saw previously. So here's another example. We don't know what the enthalpy change is for A to B, but we've been told the enthalpy change is for A to C and C to B. So just as we did in the previous example, we can, because we're going in the same direction as those arrowheads, we can add those two values together. So the enthalpy change for the reaction A to B is equal to minus 150 plus minus 100 kilojoules per mole, and that will equal minus 250 kilojoules per mole. But we don't always have that set of data. So in this next example, our Hess cycle says that we've got the reaction going from A to B. Now that is what we are trying to find, and in this case we've been told the information for the reaction between A to C and B to C. Now this is important because this means we have flipped the arrow direction for the right hand side. So in terms of Hess's law, what we're now saying is that A to C is the same as going from A to B and B to C. So the enthalpy change for A to B plus B to C is equal to the enthalpy change A to C. So if we want to know what the enthalpy change is for A to B. So we have to rearrange our equation here. If we if we subtract enthalpy change for B to C from both sides, we're left with this equation here, which we can now substitute our values into. So the enthalpy change from A to C is minus 150 kilojoules per mole, and then we're going to subtract away from that minus 100 kilojoules per mole, which leaves us with a total of minus 50 kilojoules per mole. Okay. Another example may well be that you don't know the enthalpy change value from A to C, but you know the enthalpy change from C to A, and you know the enthalpy change value from C to B. Okay. So now this time, what we can say is that the enthalpy change C to B is the same as the enthalpy change C to A and A to B. So, and we express that in this equation here. So enthalpy change of C to B is equal to the enthalpy change of C to A plus A to B. We are interested in the enthalpy change for A to B, so we rearrange this equation and say that the enthalpy change for A to B is equal to C to B minus C to A. So if we substitute in our values, okay, so C to B is minus 100 kilojoules per mole, so minus 100. Going to subtract away from that minus 150 kilojoules per mole, and that gives us a total of plus 50 kilojoules per mole. Okay. So the direction of the arrows is really important. Okay, what we're going to look at in the next couple of videos is using enthalpy change of formation data, calculating enthalpy change of formation from enthalpy of combustion data, and doing calculations using enthalpy of formation data. Okay, thank you for watching.